right. What's up, Oceanside? Looking at this title, now I can see it's quite a mouthful. I think I went with too long to be wrong. But if you want the shorter version, we're talking about scaling vulnerability research with large language models. Bit of an intro about me. I'm Caleb Gross. I got started doing offensive cyber ops for the US government. Now I do offensive security and application security in the private sector. Super interested in AI for initial access vulnerabilities. You can find me at the handle Noperator most places online. So let's go back to the basics and consider a very simple goal. What if we could find and fix all the vulnerabilities in open source software? This is a pretty ambitious goal, admittedly, but we should be. I mean, there's a reason why we all showed up at a conference that sounds like it came straight out of a sci-fi novel, right? I think it's because we all kind of have this belief at some level that we are standing at an inflection point at how we can solve classically difficult problems in the security space when leveraging AI effectively. And so it may be time to revisit long-standing assumptions about what is and is not possible when solving security in a big way. So if we were to develop a very simple pipeline for how this could work, it would look like, first of all, like locating your targets, which repos that we need to run, say, static analysis on. Dissect the code base, chunk it up into small enough pieces that an AI can perhaps help find bugs, do some triage, and then verify, report, and fix them. I've been spending the better part of the past year developing tools that can easily fit into a vulnerability researcher's workflow to help use AI to assist with some of these problems. I published a blog post a month or two ago on this tool called Slice. It's an open source tool, and maybe some of you, Aaron very kindly referenced it in his talk yesterday, so thank you. And the core idea here was, can we try to test this assumption that I think a lot of us have, which is if you arrange the right minimal pieces of context in front of a large language model, the same context that would cause me or you to say, yeah, there's clearly a vulnerability here, then maybe an AI would come to the same conclusion. So that's the core premise of Slice. It can very reliably reproduce discovery of a use after free in the Linux kernel. This is the same bug that Sean Heelan blogged about back in May in the Linux kernel SMB server implementation. And it's pretty fast and cheap. It's like $3 for a run, runs in just a couple minutes. And while I think this is very exciting and interesting, it's not terribly surprising. I have had the feeling for a while that if we just get the context right, and if the model is sufficiently capable, then it should be able to find complex vulnerabilities like this without doing dynamic analysis. So I'm gonna just read the code. But I also feel like we have sufficiently covered so far at Offensive AICon this idea of using LLMs to find bugs. I mean, I feel like we've substantiated the claim pretty sufficiently by some really excellent presentations this morning and yesterday that that's possible. So what I want to focus on is if we keep this problem in mind, if we want to find all the bugs and all the repos, we should recognize we are resource constrained. Our brains are only so big, we only have so many GPUs, there are only so many hours in the day. I am time constrained, I have 20 minutes left in this talk. So we should consider maybe the more reasonable goal, a reasonable compromise is, can we just find the highest impact vulnerabilities? Which interestingly is both a bit easier, but also quite a bit harder. Easier because the set of impactful vulnerabilities is going to be at most a subset of all of the vulnerabilities, so presumably we should be doing less work if we're just finding the high impact ones. But it's more difficult because what is impactful? How do you quantify that? There have certainly been attempts at assigning a number, a quantity, to this idea of what is impactful. We use CVSS score as one of the main ways we do that. But it's non-trivial, right? And I think what is worth spending our time on here is, let's talk specifically about target selection and also about which vulnerabilities we might choose to verify at the end of the day if we have a candidate list of 1,000 vulnerabilities that fall out of our Slice tool or whatever else we're using, right? And the core idea here that we need to latch onto is this is a matter of resource constraint, where we have to prioritize and optimize for impact while recognizing we just don't have the resources to do everything. This is a problem that we experience in a lot of ways, and we're going to talk about that more. What would be really useful here is to have a tool, like Slice with a tool for finding bugs. It would be useful to have a tool that could just intake a list of things and use an AI to just find the best thing in the list of things. That is very intentionally a very hazy, fuzzy problem, but I think it's important because it allows us to be very flexible. And ideally, since we're talking about big scale, it should also operate very efficiently even on huge input. So those are two qualities we're going to revisit throughout this talk. We just had lunch, so let's wake up a bit and talk about a fun topic: magic, witchcraft, and wizardry. We have a witch problem in the security industry. Have you noticed? It's not this kind of witch, but this kind, which is you have multiple options in front of you, and you need to decide which option to choose. And a lot of times in really difficult security problems, this is not just choosing between two options, but rather between many. There's overwhelming cognitive overload when trying to decide which target to select or which path to take when doing vuln research. And if we consider some notable statements from some of the talks we've heard so far, yesterday and today, I was scribbling down as I was listening to various talks, like, what do we pay attention to? How do we find signal in the noise? I think Kyle mentioned, I thought it was super interesting, we've done a lot of work on scanning for sensitive information in files, but not about selecting which files you should actually pay attention to. Smart targeting inside of an internal network assessment, trying to identify high-risk targets for fuzzing, voting on parallel thoughts, as we heard today, and Rukai and Oliver got 2 quotes because in the interest of our time and sanity, I thought it was a really useful way to represent how it feels to try to decide like, which of these vulnerabilities is actually worth deep diving on and validating and reporting. The OODA loop. There is a common theme between all of these problems expressed across a lot of the domains that we've heard about, and it is trying to decide which thing to do when there's an overwhelming number of options, and it requires generally a person to figure it out. And this is common to a lot of roles in the offensive, but also defense industry. I think the role of a SOC analyst is super interesting here, given that there's an overwhelming number of alerts, and the role of an analyst is to decide both when leveraging their SOAR system or their own intuition, like which one do I investigate? And this is like very difficult to do. It's very difficult to automate answers to these questions, so we rely on wizards. And this is when Rob Joyce today talked about those exploit developers that just have the magic flow. This is your seasoned expert that just has the right instinct about which items to gravitate to when there's a ton of options and it's not clear or deterministic which option you should choose. I personally encountered this problem a lot when patch diffing for end-day vulnerabilities. And so if you've ever used bindiff to examine one patch versus another, you'll arrive at this screen which shows you all the functions that changed in the patch. There are some similarity scores you can look at. You can see how much the function changed. You can kind of glance at the symbols. But it's really up to you to just follow the code smell, right? That can be effective, but at a really large scale, I would ask, do we feel like this is really working for us? SSL VPN appliances are just constantly exploited in the wild. And so I would say that relying solely on a human's intuition is like useful, and it's a very fun thing to do. It is personally gratifying. But to solve the problems at the degree of scale that we need to, I think it is insufficient. And notably, this is not a matter of what. We know what to do. We know how to fix a format string vulnerability. We know how to fix a command injection. It's not a matter of not knowing what to do. It is a matter of not knowing which to do, given that we are constrained in our resources and we have to prioritize. And that's a super difficult thing to do. I mean, you should recognize I'm repeating that theme because it is at the core, I think, of a lot of really difficult security problems, especially when you try to scale. So when it comes to finding a signal in the noise, let's consider the easiest way to do this is if you have 1,000 vulnerabilities, just try to quantify what you care about, score each one, and then sort the vulnerabilities. And that's like a pretty naive approach. It works on some level, but it also, there's a tendency to inflate toward the upper end of the scale. We see this a lot in the CVSS data set, where so far this year, there are over 200 CVEs, all with CVSS score of 10, the max score. That kind of breaks down when you still have to figure out, like, okay, well, among all the top scoring vulnerabilities, which one should I focus on? You instead could consider, what if we do a pairwise A/B comparison of every vulnerability to every other vulnerability? Large language models are pretty good at this kind of thing. They can take like data and unlike data and give you an indication of which one is most impactful or worse. They're pretty good at hot dog, not hot dog, or cancer, not cancer, if we want to get morbid like we did yesterday. But this breaks down at large scale because with a traditional sorting algorithm that might have exponential time complexity in the worst case, the calls to an LLM just explode, and an inconsistent decision early on in the sorting process can really throw off results at the end. So this maybe is a matter of just finding a better harness. So I want to make a few claims, and these are the main things that I really want you to walk away with from this talk. Firstly, this repeated theme that a lot of our classically difficult problems are probably just prioritization problems in the face of severe resource constraint, and generally we solve those problems just by putting humans' eyeballs on the problem. But the second, more important claim is that if we can transform these problems into a list-wise ranking problem, then we can use LLMs to solve these very consistently, fastly, cheaply, and to great effect. And to help illustrate this, I'm going to demonstrate a tool that's open source. It's called Rank, appropriately named. A lot of my tools are short, imperative, I'm going to follow that pattern. We're looking at a patch diff in Sonic OS. This is the operating system that underlies the Sonic Wall firewall. And so we have an advisory which says there's an off bypass. It's like very vague. An off bypass in this SSL VPN, something related to basic form code session cookies and not doing it right. And then the patch is a quite enormous patch. It's like 1,500 changed functions. When you're patch diffing, what you're hoping for is hopefully less than 10 functions change, because you can keep all that context in your head and make a pretty quick intuitive decision about which function to pursue. With 1,500, that's hours, maybe days of hunting through a patch. So instead what I did is I first used Binary Ninja to extract decompiled code for each of the functions. I did a quick summary, and given that this is a script patch, we got no symbols, did a quick summary and then ranked the resulting functions according to how relevant they seem to be to this advisory. And it works very well. The item highlighted in red is the correct function, and what we see in this right-hand mini-map is it's like your Sublime Text code map. It shows you the shape of the whole data set. You can kind of see as we sample the data set over and over, an inflection point naturally emerges in the data set, which gives us a point to distinguish the very relevant items from the ones that aren't relevant. So imagine turning your app on its side, and you would see on the left-hand side or on the top-hand side, you have the relevant items, where there's a clear spike in their relevant scores. This, honestly, it feels like magic to me. Even though I've been doing this for like the better part of a year, I just run this tool over and over just to watch it work. And I hear in the background, ping, ping, emails from OpenAI saying, your credit balance has been topped off. But it's super cool. And it's a CLI tool, so you can just pipe it into your normal Unix pipeline. That's the way I like to work, and I assume a lot of others do too. This is using document ranking. It's just like doing a Google search, asking for the best pizza in San Diego, where your documents are all restaurants or web pages or whatever. But instead, our advisory is our search query. Our changed functions in this patch diff are the documents, and the most relevant ones go to the top. So we sample the data over and over. We find the items that most often rise to the top when they are relatively ranked in a small batch. And we collect all of those top performing items. We throw away the ones that aren't relevant. We double down on the ones that clearly have some signal. And we recurse and rank those. And we keep closing the gap until we have a highest ranking item. This is clearly illustrated by choosing a domain name, for instance. So like I saw someone on Twitter say, I want a mathy domain name. And that's a weird problem to try to solve. It's very fuzzy, like what makes a domain name mathy? I don't know. It's hard to objectively score that, right? But you can say relatively which domain name is mathier than all the others. So if we take a small data set of like 25 TLDs, split them up into 5 groups of 5, use a large language model. So we make 5 calls to an LLM, just ranking the small batches. And we will see that .xxx goes to the top, mathy apparently. .simp, .xyz. If we run a few more trials, so shuffle the whole data set, resample it over and over, see which items come to the top, we see that .simp and .xyz consistently, no matter which sample they land in, they go to the top. The data is beginning to speak to us through the LLM. Those are the items that are most relevant. And if we were to graph this, we would see, yeah, that .simp, .xyz are there on the top. So this is the same shape of graph that I was showing in the tool demo a moment ago. If we run a few more trials, we will see that we can see the shape of the data in higher resolution. So that there's not just a linear relevance curve, but there's a clear inflection point where you can see the items that are relevant that are clearly distinguished from the ones that are not. And we can see this even more clearly if we look at the rate of change. So think of like second derivative or acceleration. You can see that near the top, the score increases more rapidly, which gives us a clear cutoff point to say like, okay, probably everything under this line, we toss out. Everything on top, we probably want to double down and recurse and start ranking those more aggressively. So if we take the whole TLD data set, so roughly 600 TLDs, and we throw it into this ranking tool, this is operating in real time. It's very fast, it's super token efficient, so it probably costs like a dime to run this. We see that .academy, .university, .institute go to the top. If you don't want that academic leaning, you could just refine your prompt and say, I want the hard math stuff, so it might give you .int, very interestingly, or .plus. We should address the namesake of this talk. The computational complexity here allows us to really tackle the scale problem. Since if we're using a traditional sorting algorithm like merge sort or quick sort, we're making a very expensive guarantee about the data set that we don't need to make for a lot of security problems. That is, we don't need to guarantee the entire ordering of the whole data set, but rather we just need to find the top items. And if we recognize that, then we can use some pretty useful tricks, like cutting the data set in half every time, or even converging early and not running more trials. If we see that the position of that inflection point stabilizes, this is really powerful because there is no fine-tuning here. There's no domain-specific models. There's none of that. It's just an off-the-shelf open weight or a frontier model. Just hit the API. The key point here is the complexity of the entire problem is localized in just that small call to an LLM for 10 items at a time. That is, if it can solve and rank your data 10 items at a time, then it can rank 10,000. We can also compare unlike items. So a SOC analyst can rank their SOC alerts and get a meaningful answer to the question, like, which one is more important? This weird phishing email that I got, or a brute force attempt on my public login form? You could also feasibly employ this as an explicit decision-making framework in an offensive workflow. Consider that smart targeting and operating inside of an internal network is constantly you taking all of your context available to you and deciding would it make sense to go deep or keep looking broadly, which target would bring me toward my goal. And given that this is a large language model, it can just explain itself, which is a very useful property of using large language models for this purpose. Let's look at a few case studies. So if we go back to the original problem, like we want to find all vulnerabilities, or at least the most impactful ones, then our first job is to try to identify which target do we want to look at. And in this case, I just took the top 2,700 C and C++ and Python repos, and I asked which of these is widely used. Maybe it's doing security sensitive or safety critical stuff, parses untrusted input. What are the kind of targets that I feel like I would want to consider if I were intuitively navigating this data set, and can an LLM help me rank them? And when we look closely at the results, unsurprisingly, Linux kernel goes to the top. Redis is up there too. There was just a CVSS score of 10 RCE that dropped in Redis last night. OpenPilot, I was very pleased that OpenPilot landed in this data set. I was hoping it would. That's an open source autonomous driving framework. Chromium, let's take the top item, Linux kernel, and say, within this project, what are the subsystems that we would actually want to target for vulnerability research? So if we look at the maintainers file, we're looking at like 3,000 distinct subsystems in the Linux kernel, where we can ask roughly the same question. Which of these is most likely to allow something nasty if I were to be able to exploit it? Is there something that crosses trust boundaries or reads data off the network? And we see KVM, NFS, KSMPD, which has been the focus of a lot of research over the past year. Wi-Fi drivers, that's the kind of stuff we would want to see. And I want to be clear, the points I'm making here is not that an LLM can do this and you never could, right? Because the idea is just that it's super expensive and not feasible to keep humans at the gate of making prioritization decisions like these if we want to scale really aggressively. So at least what we would want to see naively is, are we at least getting the kind of results that I feel like I would want to see if I were the one ranking this data set? And I feel like in a lot of cases, almost unilaterally, it's like, yeah, and if I don't see exactly what I want, I just tweak the prompt until the data is starting to take the shape that I would expect it to. If we were to go back to that example of CVSS scores, there are over 200 vulnerabilities that all are scored as 10. If we run this through a ranking data set, we will see the top items are RCE and Cisco appliances. You can see item 11 is that Redis use after free RCE that I just mentioned. The idea here is, instead of just having to manually browse a list, and maybe you can overlay other data points like EPSS scores, but you're still solving the same kind of problem, trying to quantify something that really wants to just inflate toward the upper end of whatever scale you give it. And in this case, instead of seeing post-auth command injection on IP camera, which is a lot of the stuff you will see if you look at the top CSS scores, you see items that are the kind of things I would really be concerned about. So a couple of closing thoughts. I think what I would really like to communicate here is please examine the shape of your hard problems that you're trying to solve and ask, might it be feasibly solved with an AI if you were just to try to approach it from a different angle or transform it into a kind of problem that we already know how to solve and that a large language model can do at scale quite effectively. I have felt for a while that I'll just look for models to get better rather than improving my scaffold or harness. And I'm starting to feel like a lot of models, open weight models, are quite capable for the kind of problems we need to solve. And so there's a lot of super impactful work that we could do right now if we just recognize the kind of problem we have and try to solve it appropriately. So the things we have that work are build-free analysis at scale using slice. You don't have to compile the code or anything, just read the code, and it works pretty well. And then ranking a data set and using convergence detection to operate really efficiently. Other areas that I still want to apply more focus to is dynamic verification of those results. And also the kernel project has a bit, unfortunately, been a sacrificial guinea pig for a lot of AI-assisted disclosure. I've seen some encouraging results just in the past few days. That Daniel Stenberg has gotten some better results, but he's somehow still patiently reading through and is saying, yeah, you know what, AI actually helped here, so thank you. It was Joshua, I don't recall his last name. But that was really cool, kind of a milestone moment. You don't have to take my word for any of this. The tools are both open source, rank and slice. I'm super excited about where this is going. I feel like I can tangibly feel being at an inflection point in the industry. Thanks so much for having me talk. I would love to entertain questions now or later. Thank you so much.